In 2018, NASA published a technical study examining construction materials for long-duration human habitats on Mars. The problem they were solving is not simple. Mars has no timber, no Portland cement supply chain, no glass fiber insulation, no power grid to run HVAC systems. A habitat on Mars has to be built from what is available on the surface and has to maintain a livable internal temperature in an environment where the average outside temperature is -60 degrees Celsius. The material that kept appearing in their analysis as structurally viable, thermally effective, and buildable with minimal processing was a compressed mixture of local regolith, essentially Martian soil, bound with a small amount of water and pressure. A brick, an earthen brick. The oldest manufactured building material in human history. NASA was, in technical terms, rediscovering adobe. Adobe brick construction has been continuous for approximately 9,000 years. The earliest confirmed examples come from the Neolithic site of Ain Ghazal in what is now Jordan, dated to around 7,000 BCE. Adobe buildings in Yemen, in New Mexico, in Iran, in Mali, are still occupied today, not as museums, not as preserved ruins, as functioning homes where people live, cook, sleep, and raise families. Some of those buildings are several hundred years old. The walls are original. The insulation value of a correctly built adobe wall, measured in the same R value per inch that gets printed on the packaging of fiberglass bats at Home Depot, is not remarkable. Adobe does not win on R value per inch. What Adobe does that no insulation product you can buy in a bag or a roll can replicate is something called thermal mass. The ability to absorb heat during the day, store it, and release it slowly at night. And that property, in climates with significant day-night temperature swings, outperforms conventional insulation in ways that do not show up in the R value number, but show up very clearly in your utility bill. I want to tell you exactly how this material works, where it came from, how to make it with soil from your own property at essentially zero cost, and why the modern building material industry has spent 70 years finding ways not to discuss it. What adobe is, and why the physics work. Adobe is unfired earthen brick. The word comes from the Arabic al-tuba, meaning the brick, which passed through Spanish into English via the American Southwest. But the material itself has no single geographic origin. It developed independently on every inhabited continent where soil conditions permitted. Because the logic is simple. Wet earth, shaped, dried in the sun, stacked with wet earth as mortar. The soil composition for good adobe is not exotic. You need roughly 70% sand, 20 to 30% clay, and some fibrous material. Straw is traditional, but dried grass, animal hair, or shredded plant matter all function identically. The sand provides structural bulk and prevents cracking. The clay is the binder. When wet, clay particles align and form hydrogen bonds with water, creating a plastic material that can be shaped. When dried, those bonds tighten, and the clay matrix locks the sand particles into a rigid composite. The fiber controls shrinkage, cracking during drying, distributing stress across the matrix rather than allowing it to concentrate into a single fracture. This is not primitive chemistry. This is particle size distribution, binder chemistry, and fiber reinforcement. The same conceptual framework used to engineer modern concrete, fiber-reinforced polymer composites, and structural insulated panels. The Neolithic builders who developed adobe did not have the vocabulary, but they had thousands of years of empirical refinement. They knew which soil worked and which did not. They knew how much straw to add, They knew the brick had to dry slowly in shade before full sun curing. That accumulated knowledge is the engineering. The thermal performance of adobe comes from its density. A standard adobe brick is dense approximately 100 to 120 pounds per cubic foot, compared to about 30 to 40 pounds per cubic foot for a framed wall cavity filled with fiberglass insulation. That mass has a specific heat capacity of roughly 0.2 British thermal units per pound per degree Fahrenheit. A typical 18-inch thick adobe wall contains enough thermal mass to absorb the entire heat gain of a summer day and release it through the cool of the night, keeping the interior within a few degrees of a stable mean temperature without any mechanical assistance. This is called the thermal flywheel effect. A lightweight framed wall with R19 fiberglass insulation will resist heat flow. But when the resistance is overcome, the interior temperature spikes rapidly because there is no mass to absorb the load. An adobe wall with an equivalent or lower R value per inch will not let the interior temperature spike because the mass is absorbing the incoming energy and buffering it across time. The adobe wall is slower, and in building science, slower is often better. The University of New Mexico, which has studied adobe construction extensively over several decades, has documented that an 18-inch adobe wall in a desert climate with a 30-degree day-night temperature swing maintains interior temperatures within a 5-degree range throughout a 24-hour cycle. A code-compliant framed and insulated wall in the same climate shows interior temperature variation of 12 to 15 degrees under the same conditions. Same energy input from the sun, different material response. The adobe wall wins on comfort and energy use, not on the R value label. 9,000 years of continuous use. The site of Ain Ghazal, near modern Amman, Jordan, is one of the largest known Neolithic settlements in the Near East. Excavations beginning in the 1970s revealed mud brick construction proto-adobe dated reliably to approximately 7,250 BCE. This was not a primitive temporary structure. This was a planned settlement with multi-room buildings, plaster floors, and evidence of construction techniques that suggest accumulated craft knowledge passed between generations.
That is good work.
Jericho, arguably the world's oldest continuously occupied city, shows adobe construction in its earliest occupation layers, dated to around 9,000 BCE. The walls of ancient Jericho were not stone. They were sun-dried mud brick, built thick enough to serve as defensive fortification and insulation against the Jordan Valley heat simultaneously. The same wall did two jobs at once, and it did them with soil from the ground it stood on. In ancient Egypt, adobe was the standard construction material for everything that was not a royal monument or a temple. The workers who built the pyramids at Giza lived in a purpose-built town of adobe housing constructed around 2500 BCE. That town, excavated by archaeologist Mark Lenner beginning in the 1980s, shows standardized brick dimensions, organized street grids, and building techniques that indicate professional construction labor, not improvised shelter.
It smells so
The pharaohs
good.
built their monuments in stone because stone was permanent and symbolic. Adobe was for the living because adobe was practical, comfortable, and abundant. The Book of Exodus records the Israelite slaves in Egypt making bricks of straw and clay, a direct reference to the adobe production process that was central to Egyptian construction economy. Whether or not the historical narrative is literal, the material description is accurate. Egyptian administrative records from the New Kingdom period include production quotas for mud brick manufacture, delivery schedules, and quality control specifications. This was an organized industry, not a folk craft. In the American Southwest, the ancestral Puebloans built multi-story adobe structures at sites like Pueblo Bonito in Chaco Canyon between roughly 850 and 1150 CE. These were not single-family homes. They were apartment complexes, some reaching 4 and 5 stories, housing hundreds of people. The adobe walls at Chaco Canyon are still partially standing. The thermal performance of those thick earthen walls in an environment that sees summer temperatures above 95 degrees Fahrenheit and winter nights below freezing maintained a habitable interior environment without any heating or cooling system beyond the mass of the walls themselves. The Great Mosque of Djenné in Mali is the largest mud brick structure on Earth. The current building dates from 1907, though it occupies the site of a mosque built in the 13th century. It is maintained annually by the entire community of Djenné in a traditional replastering ceremony that has been continuous for centuries. Because in a climate with heavy seasonal rainfall, adobe requires periodic surface maintenance. But that maintenance costs nothing in materials. The soil is local. The labor is communal. The building has stood, with maintenance, for over 700 years.
The thermal
The
conductivity
NASA connection
seems lower
and
than
what it
projected
actually
in this
means.
quadrant.
That correlates
When
with
NASA
the
engineers
increased
began
porosity
seriously
readings.
modeling
We need to
construction
adjust the
scenarios
centering
for Mars
parameters.
surface habitats in the 2000s, the constraints they faced were clarifying. You cannot ship building materials from Earth to Mars economically. The cost per kilogram of payload delivered to the Martian surface is measured in hundreds of thousands of dollars. Any viable Mars habitat has to be built using what NASA calls in situ resource utilization, abbreviated ISRU. Use what is there. Process it minimally. Build from it. Martian regolith, the loose surface material covering most of the planet, is a mixture of silicate minerals, iron oxides, and fine particulate matter with clay-like particles in its composition. It can, under the right conditions and with appropriate binders, be compressed into a construction material that behaves in ways analogous to adobe. NASA's Jet Propulsion Laboratory and the Center for the Utilization of Biological Engineering in Space at UC Berkeley both published research between 2015 and 2020 examining regolith-based brick formation. One study used chitin, a biopolymer derived from crustacean shells, as a binder for Martian regolith simulant, producing bricks with compressive strength comparable to ordinary Portland cement concrete. The thermal properties of thick earthen walls are specifically relevant to Mars because the planet has extreme temperature swings, up to 100 degrees Celsius between day and night at some latitudes, and essentially no atmosphere to buffer them. The thermal mass principle that makes adobe effective in desert environments on Earth applies with even greater force on Mars, where there is no HVAC industry to fall back on, and no utility grid to power one. None of this is NASA endorsing adobe brick construction for your backyard in any direct sense. What it is independent confirmation by some of the most rigorous materials engineers on Earth that the thermal and structural principles underlying earthen brick construction are sound enough to stake human lives on in the most demanding environment humans have ever planned to inhabit. That is a meaningful validation of 9,000-year-old technology, arriving from a direction nobody expected. The irony is precise. The building material that NASA is studying for humanity's first extraterrestrial habitats is the same building material that American building codes in most jurisdictions effectively prohibit for new residential construction. Not because it does not work, because it does not fit the regulatory framework built around manufactured products with standardized specifications, liability insurance chains, and manufacturer warranties. Adobe cannot be certified by a manufacturer. You cannot call the Adobe hotline when something goes wrong. The building inspector cannot look up its load-bearing value in a product data sheet. And so, it is excluded. And contractors build with framed walls and fiberglass bats. And homeowners pay utility bills that an Adobe wall would have made unnecessary. How to make Adobe brick from your own property. The soil test comes first. Not every soil makes good Adobe, but most subsoil, the layer below the topsoil, below the organic material, has enough clay content to work with. You can test this in 10 minutes with no equipment. Take a handful of subsoil, moisten it until it reaches the consistency of stiff cookie dough, and roll it into a cylinder about 1 inch in diameter and 6 inches long. Hold it horizontally from one end. If it holds itself out for 2 inches or more before breaking, your clay content is sufficient for Adobe.
Too much sand.
If it breaks immediately, you need to
collapse.
source or add clay. If it bends without breaking and feels sticky, your clay content is high and you need to add more sand. The standard mix ratio for stable Adobe is approximately 70% coarse sand to 30% clay by volume. In practice, if your subsoil tests well, you can use it directly with the addition of straw and water. Mix the dry ingredients first, soil and any sand amendment. Then add water incrementally until the mass reaches a consistency where it holds a shape when squeezed, but releases cleanly from your hands. The straw goes in last, mixed by foot treading on a tarp or in a shallow pit, at roughly 1 part straw to 10 parts soil mix by volume. Traditional molds are simple. A rectangular wooden frame, bottomless, set on a flat surface. Standard Adobe dimensions in the American Southwest tradition are approximately 10 by 14 by 4 inches, but the exact dimensions are not critical. What matters is consistency across a batch so that your wall courses lay level. Fill the mold, pack it firmly to eliminate air pockets, strike the top flush with a board, and lift the mold straight up. You now have a green, Adobe brick green, meaning uncured. Green bricks are fragile. They go onto a flat surface in a shaded area for the first 2 to 3 days, turned once after 24 hours to expose the bottom face to air. After 3 days in shade, they can move to partial sun. Full sun curing in dry weather takes 10 to 14 days. The brick is ready when it is dried completely through. No cool or damp feeling at the center when you break a test brick in half. A properly cured Adobe brick has a compressive strength of approximately 300 to 600 pounds per square inch, which is adequate for single-story and many two-story construction applications. The cost per brick in materials is essentially zero if your subsoil has adequate clay content. A bale of straw for fiber costs approximately $8 and provides enough material for several hundred bricks. Water is the only other input. A person working alone can produce 60 to 80 bricks per day using a 2-brick mold. A crew of 3, 1 mixing, 1 molding, 1 handling cured bricks, can produce 200 or more bricks per day. Compare that to concrete masonry units, standard cinder blocks at approximately $2 per unit at current retail prices. To build a 16 by 20 foot room with 8-foot walls using concrete block costs roughly $1,200 in block alone, before mortar or labor. The same room in Adobe, using soil from the building site, costs the price of straw and the time of the people making it. NASA calls this in situ resource utilization. Traditional builders called it common sense.
The face of American
What the building
housing
industry
was
did
changed
not want
forever.
to standardize. Adobe construction in the United States did not disappear because it failed. It was the primary residential construction method across the American Southwest for centuries before and after European contact. The Spanish colonial buildings in Santa Fe date from the early 1600s. The Pueblo structures at Taos have been continuously occupied since approximately 1000 CE. These are not historical anomalies. They are 400 and 1,000 years of performance data, respectively, in a climate that is not forgiving. The marginalization of adobe in mainstream American construction accelerated in the post-World War II period for the same reason that natural bitumen waterproofing and linseed oil wood treatment were marginalized at the same time. The industrialization of the building supply chain rewarded standardized, manufactured, patentable products. Dimensional lumber, manufactured in mills to standardized sizes, could be shipped, inventoried, and written into a building code with precision. Adobe, made from local soil with local labor, could not be inventoried, could not be shipped profitably, and could not be sold with a manufacturer's warranty. The industry that formed around manufactured building products had both the incentive and the mechanism to shape building codes in ways that required their products and excluded alternatives. This is not a secret. The influence of industry trade associations on model building codes is extensively documented in construction history literature. The result is that in most American jurisdictions, building a new home from adobe requires an engineering approval process that adds cost and time roughly equivalent to the savings from the free material. The regulatory friction makes it uneconomic, and uneconomic things disappear from practice, one generation at a time. New Mexico, Arizona, and California are partial exceptions. The New Mexico Adobe and Rammed Earth Building Code, first adopted in 1991, is the most comprehensive framework for permitted adobe construction in the United States. It is not a coincidence that these are the states with the longest uninterrupted adobe construction tradition and the strongest advocacy from preservation and vernacular architecture communities. They had enough institutional memory of how the material actually performed to push back against the manufactured product default. The situation NASA faces on Mars, build from local material or do not build at all, is the situation most of human history faced until approximately 1950. Before the global supply chain for manufactured building products existed, people built from what was locally available. In Mesopotamia, that was mud and reed. In the desert Southwest, that was adobe soil. In Scandinavia, that was timber and turf. Every one of those materials was refined over centuries into a high-performance system appropriate to its specific climate. And then the supply chain arrived with a single set of standardized materials optimized for the economics of a factory in a particular place and sold everywhere, regardless of whether the climate called for it. I want to leave you with a specific number, because numbers are harder to dismiss than arguments. The average American household spends approximately $2,200 per year on heating and cooling. The primary driver of that cost is building envelope performance. How much heat the walls, roof, and windows allow in and out. A well-built adobe home in a climate with significant day-night temperature variation requires, in many cases, no mechanical heating or cooling at all for the majority of the year. The thermal mass of the walls does what the HVAC system does, for free, using physics that have been understood for 9,000 years. The material to build those walls costs what your subsoil costs, which is nothing. The knowledge to build them is not proprietary. It is in the archaeological record, in the building traditions of New Mexico and Yemen and Mali and Iran,
we need to ensure the density
in the technical
here matches
reports
the
of soil
specifications for the
scientists
load-bearing walls over
and
there.
vernacular
Understood.
architecture
The structural
researchers,
integrity is paramount.
and now in the engineering studies of NASA researchers planning humanity's first extraterrestrial settlement. The reason Adobe is not in the home improvement section of your hardware store is not that it does not work. It is that you cannot sell it. You cannot put local subsoil in a bag with a brand name, a UPC code, a manufacturer's warranty, and a sponsored result at the top of a search page. It is soil and straw and water and time. What cannot be sold cannot be marketed. What is not marketed does not exist for most homeowners until they go looking for it. Now you know where to look. Your subsoil is already there. The straw costs $8. NASA has confirmed the physics work all the way to Mars. They work in your backyard, too.